Howdy. FIRST.org. Compact electron accelerator reaches new speeds with nothing but light. Check out these pictures. Let's read first. An image from a simulation in which a laser pulse red. Obviously, this one here, red. So the direction is this way. Drives a plasma wave, accelerating the electrons in its wake. The bright yellow spot is the area with the highest concentrations of electrons. In an experiment, scientists used this technique to accelerate electrons to nearly the speed of light over a span of just 20 centimeters. This might be a shock wave. And you have to imagine this in 3D. Of course. But anyway, let's read this. I tried to read it. Scientists harnessing precise control of ultra-fast lasers have accelerated electrons over a 20 centimeter stretch to speeds usually reserved for particle accelerators the size of 10 football fields, like CERN or such. The team at the University of Maryland, UMD, headed by Professor of Physics and Electrical and Computer Engineering Howard Milchberg, in collaboration with the team of Jorge J. Roca at Colorado State University, achieved this feat using two laser pulses sent through a jet of hydrogen gas. The first pulse tore apart the hydrogen, punching a hole through it and creating a channel of plasma. The channel guided a second higher power pulse that scooped up electrons out of the plasma and dragged them along in its wake, accelerating them to nearly the speed of light in the process. With this technique, the team accelerated electrons to almost 40% of the energy achieved at massive facilities like the kilometer-long Linear Coherent Light Source LCLS, the accelerator at SLAC National Accelerator Laboratory. The paper was accepted to the Journal Physics Review X on August 1st, 2022. Physical Review X. That sounds interesting. Or maybe it's just Roman and then it's, what is it, 10 something, 15, whatever. This is the first multi-GeV electron accelerator powered entirely by lasers, says Milchberg, who also affiliated with the Institute of Research Electronics and Applied Physics at UMD. And with the lasers becoming cheaper and more efficient, we expected our technique will become the way to go for researchers in this field. Yes. Play with plasma. Motivating the new work are accelerators like LCLS, a kilometer-long runway that accelerates electrons to 13.6 billion electron volts. The energy of an electron that's moving at 99.9999993% of the speed of light. LCLS predecessor is behind 3 Nobel Prize-winning discoveries about fundamental particles. Now, a third of the original accelerator has been converted to the LCLS, using its super-fast electrons to generate the most powerful X-ray laser beams in the world. Scientists use these X-rays to peer inside atoms and molecules in action, creating videos of chemical reactions. These videos are vital tools for drug discovery, optimized energy storage, innovation in electronics, and much more. Maybe war, weaponry. They don't talk about this. Accelerating electrons to energies of tens of GeV is no easy feat. SLAC's linear accelerator gives electrons the push they need using powerful electric fields propagating in a very long series of segmented metal tubes. If the electric fields were any more powerful, they would set off a lightning storm inside the tubes and seriously damage them. A lightning storm. Being unable to push electrons harder. Researchers have opted to simply push them for longer, providing more runway for the particles to accelerate. Hence the kilometer-long slice across Northern California. To bring this technology to a more manageable scale, the UMD and CSU team worked to boost electrons to nearly the speed of light using, fiddling enough, light itself. The goal ultimately is to shrink GeV scale electron accelerators to a modest size room, says Jaron Schrock, a graduate student in physics at UMD and co-first author on the work. You're talking kilometer scale devices. You have another factor of 1,000 stronger accelerating field. So you're talking kilometer scale to meter scale. That's the goal of this technology. Yeah, meter. That's a gun. I hear you, scientist. Creating those stronger accelerators. Who thinks stuff like that? It's science. Anyway. Creating those strong accelerating fields in the lab employs a process called laser wake field acceleration, in which a pulse of tightly focused and intense laser light is sent through a plasma, creating a disturbance and pulling electrons along in its wake. So, there are basically sea-pinching laser beams, I would say. The torus, the donut, minimal first distinction, the Word of God. The dots of the squatter man. I think it works in a way like that. But anyway, maybe we could read on. You can imagine the laser pulls like a boat. Alright, says Bo Miao, a postdoctoral fellow in physics at the University of Maryland and co-first author of the work, as the laser pulse travels in the plasma. Because it is so intense, it pushes the electrons out of its path, like water pushed aside by the prow of a boat. Those electrons loop around the boat and gather right behind it, traveling in the pulse's wake. Yeah, torus. What goes around comes around. Laser wake field acceleration was first proposed in 1979 and demonstrated in 1995, but the distance over which it could accelerate electrons remained stubbornly limited to a couple of centimeters. What enabled the UMD and CSU team to leverage wake field acceleration more efficiently than ever before was a technique What? Yeah, sorry. I don't know what happened. I didn't touch the phone or whatsoever. It just ended, jumped off. Anyone listening? I bet. Anyway, Let's start at the beginning of the sentence at least. What enabled the UMD and team to leverage wake field acceleration more efficiently than ever before was a technique the UMD team pioneered to tame the high energy beam and keep it from spreading its energy too thin. Their technique punches a hole through the plasma, creating a waveguide that keeps the beam's energy focused. Sounds in a way like a black hole, of which is coming out a ultra strong beam which can expand for hundreds of thousands of light years. Yeah, there are no black holes. There's just pinches. Squattermans all over the place. A waveguide allows the pulse to propagate over a much longer distance. Schrock explains. We need to use plasma because these pulses are so high energy, they are so bright, they would destroy a traditional fiber optic cable. Plasma cannot be destroyed because, in some sense, it already is. What? That's quite an oxymoron. Like we have a new tool. It's plasma. Like it's already destroyed stuff. Very important. Without this, we couldn't do. But it's already destroyed. What? Anyway, their technique creates something akin to fiber optic cables, the things that carry fiber optic internet service and other telecommunication signals out of thin air, or more precisely, out of carefully sculpted jets of hydrogen gas. Yes, maybe not of thin air. They did a little bit something to it, obviously. The conventional fiber optic waveguide consists of two components: a central core guiding the light and a surrounding cladding preventing the light from leaking out. To make their plasma waveguide, the team uses an additional laser beam and a jet of hydrogen gas, which is the thin air. As the additional guiding laser travels through the jet, it rips the electrons off the hydrogen atoms and creates a channel of plasma. The plasma is hot and quickly starts expanding, creating a lower density plasma core and a higher density gas on its fringe, like a cylindrical shell. Yeah, double layers, Birkeland currents and such. Then, the main laser beam, the one that will gather electrons in its wake, is sent through this channel. The very front edge of this pulse turns the higher density shell to plasma as well, creating the cladding. It's kind of like the very first pulse clears an area out, says Schrock. And then the high intensity pulse comes down like a train with somebody standing at the front throwing down the tracks as it's going. This doesn't make any sense to me because the tracks are not moving. What? Train is okay, and you throw it and stare just on the ground as far as you threw it because the tracks are still there. Train is gone. I don't know. Anyway, he's doctor. He knows what he's talking about. I'm not interfering. Using UMDs, I'm here to learn. Sorry. Using UMD's optically generated plasma waveguide technique combined with the CSU team's high-powered laser and expertise, the researchers were able to accelerate some of their electrons to a staggering 5 GeV. This is still a factor of 3 less than SLAC's massive accelerator and not quite the maximum achieved with laser wake field acceleration. That honor belongs to a team of Lawrence Berkeley National Labs, or Christian Birkeland, and some others. Sapphire Project. Anyway, however, the laser energy used per GeV of acceleration in the new work is a record and the team says their technique is more versatile. It can potentially produce electron bursts thousands of times per second, as opposed to roughly once per second, making it a promising technique for many applications from high energy physics to the generation of X-rays that can take videos of molecules and atoms in action like at LCLS. Now that the team has demonstrated the success of the method, they plan to refine the setup to improve performance and increase the acceleration to higher energies. Right now, the electrons are generated along the full length of the waveguide, 20 centimeters long, which makes their energy distribution less than ideal, says Meow. We can improve the design so that we can control where they are precisely injected, and then we can better control the quality of the accelerated electron beam. Yes. While the dream of LCLS on a tabletop is not a reality quite yet, the authors say this work shows a path forward. There's a lot of engineering and science to be done between now and then, Schrock says. Traditional accelerators produce highly repeatable beams with all the electrons having similar energies and traveling in the same directions. We are still learning how to improve these beam attributes in multi-GeV laser Wakefield accelerators. It's also likely that to achieve energies on the scale of tens of GeV, we will need to stage multiple Wakefield accelerators, passing the accelerated electrons from one stage to the next while preserving the beam quality. So there's a long way between now and having an LCLS type facility relying on laser Wakefield acceleration. Yeah, we actually made it to the end. Let me show you something. That's some 5-year-old, this video. I just took the first, which came. Rust cleaning laser, 5 years ago. And you can just buy a machine like this, I guess, if you have money enough. Go to the shop, buy it, and go home and do this.
The handheld rust removal laser, which makes rust literally evaporate. I could not believe what I was seeing when I first came across this device on YouTube. A laser that cleanly removes rust and other surface contaminants without eating away the metal underneath. When aimed at a metal surface, the dirt layer and any oxides underneath will absorb the energy and evaporate. The metal underneath will not absorb the laser energy, leaving nothing but a clean surface ready for welding and painting. So how does it work? Well, the system uses short pulses of laser light at 1000 watts, producing microplasma bursts along with thermal pressure and shock waves to sublimate the rust and separate it from the metal.
You can amplify this, like scale it up. Yeah, maybe it's hard to believe. But let me put it like that. In those places where we experience the phenomena called night, which are quite many places on Earth. Just go out there and watch at the stars. There are many. They're all in a way connected with each other. Cosmic Barton currents and such. Light speed is no limit or whatsoever. There are many things which are much faster than light. Already the things which spin around, like in atoms, they are already faster than light. But anyway, what do you think? How much energy is providable by the universe? how much energy our sun can provide in a, like, let's say a 10x flare. There's quite much energy. How Earth will take it in, we will maybe discover that too. So there were like those scientists playing around with lasers. And here, this machine 5 years ago, some dude saw a video on YouTube, went to the shop and bought a machine. A laser. And just think about Earth's surface. Things like surface conductivity anomalies, magnetic anomalies, like I am talking about, imprinted in the crust of Earth. They will affect weather patterns as our magnetosphere is weakening. And their influence into the weather, it will just increase. I have been talking about this many times. And let's see, I wrote actually to some Swiss glacial institute or something. And I got an answer because I was asking, I saw this picture from this glacier with those red streaks in it. Let me show you. I made a funny picture. Iron deposits in the glacier ice? That's the question. What are those red streaks? And I found them because there was a fire on the mountain. Glacier 3000 was burning. Back in the old times, it was just called Le Diablerie, and I have been there. It turned out I know the place. I have been there as a kid. And I also found the Iron Well, which is in a way proof that there is really a possibility that there is iron containing water coming out of the earth. Not too far away. It's approximately 33 kilometers. Yeah, that's the funny picture I was talking about. And I was sending him this picture here. He thought that it might be algae. Maybe, I don't know. That's why I'm asking. I've been reading about algae. There's like a few places on Earth. Is it in Antarctica where you have like this red ice and stuff? Let's see. I really hope that there will be some conversation. And why I talk about this is the reason. Iron reacts strongly to magnetic fields. I'm still thinking that is there a possibility if there's a glacier which every now and then has some eruptions with iron containing water? This would mean that there would be like iron just in great abundance spread all over the place within the glacier. Hence, it is really at the surface. Does those things mean anything? I think they do more and more because our magnetosphere is weakening. Weather is entirely driven electrically, as I showed in this earlier map about the surface conductivity anomaly in Scandinavia. So, we started off with those lasers, minimal first distinction. I don't, maybe I show you still one picture. And if you're watching rocks, you can find things like that. There's like molten metal tetrahedrons, quartz craters. Like here, welded It's probably not the best picture quality since I have zoomed in quite heavily. Heavenly. Molten metal on top of a rock. Craters. They really look like they got burned into the rock. They're not some rusty. There's no rust somehow. I think there's manganese, maybe. I don't know. I really would like to know, but they don't tell because they are silent. Well, anyway, lasers and plasma rocks. What do they have in common? Very much electricity. Very interesting times. Yeah, they want to get it down to 1 meter. Seems practical. But anyway, I leave it here. Thanks.